Okay, we have 20 people who have joined at the moment. We'll give it just a few more minutes. In any case, all of you who are online already, please don't forget to update your clone of the repository, because I've added some material yesterday evening. In fact, even this morning I added uh, one uh, one link to a video in the ParaView raytracing.pdf document. So if you want that to be up to date, please update your clone with a Git pull. We're going to spend most of the day, most of the morning on Jupyter.cscs.ch. So that will be easier rather than doing a client server connection. Actually, some of you who want to repeat those examples directly with ParaView itself on your local installation, you should be able to do that as well. Okay. In fact, I'm going to start my allocation on Jupyter, and I'm going to share my screen just to show people again how to do the allocation of the Jupyter Hub server. All right, so this is the Jupyter Hub front page, and what you should remember is the advanced reservation here, which should be set to visual_course. The Jupyter Lab version, you should select the 2.02 version. And then over here in the duration, the default is 1 hour. I've set that to 4 hours for this morning so that I will have my server for the entire morning. And once you're done with this, you can just launch the Jupyter Lab, and it will get you an allocation in a few minutes. Okay, so I will now start my presentation. So good morning, everyone. Thanks to all of you for attending this seminar. Today we're going to talk about advanced rendering and visualization. Perhaps I should briefly show you the schedule of the day. So I'm back here again. This is the page announcement of the course on the CSCS website. Today we are October 13th, so Tuesday. From 9 to 10, we're going to talk about photorealistic rendering for 3D visualization. So a few keywords: ray tracing, path tracing, ambient occlusion. We're going to see all those different techniques applied in ParaView within the Jupyter Lab notebook. And then after the break, we'll do physically based rendering, which is something a little bit different, but still very attractive. We'll have 2 breaks at 10 o'clock, but I should remain online most of the time. This should be an opportunity to ask questions and to try some of the techniques shown. And then at 11 o'clock again, we'll have more Q&A time. And yesterday, somebody pointed out that I have forgotten to discuss the import of NumPy array into Python. And I apologize for this. I did a quick intervention yesterday evening. I think some of you might have followed that already. And then there was one question which I actually failed to answer. This was just because I was tired. I used the wrong variable names to save the data. So this morning, I have an updated script to demonstrate how to import NumPy arrays into ParaView, and we will try to fit that in one of the breaks. All right. So on to photorealistic rendering for 3D visualization. There. Now, I've actually slightly changed the title to advanced rendering because not everything is photorealistic rendering. I'd rather call it advanced rendering. Let's see why. Now, you know, the famous joke, CFD, it shouldn't be colorful fluid dynamics, but it's really computational fluid dynamics. So the use of visualization should not really be focused on making something pretty, but rather on making something useful to debug a simulation, understand what is going on in your simulation, and then really do some analysis, query for properties, etc. This should be your first goal in any case in visualization. Of course, if you can do more, if you can both understand and depict a particular physical phenomena with your simulation and do something that stimulates discussions, then why not? So this is where advanced rendering would fit in. Provide enhanced perception, give you ways to clearly see the data, and often, in fact, in HPC, we have too many data points. So the use of advanced rendering should be really concentrated on enhancing the perception, getting rid of what is not so interesting for the visualization of the phenomena, and concentrate on the important point and regions in space where something nice is happening. So we will see an example about this. The first example is a technique called screen space ambient occlusion, also with an acronym SSRO. All right. Now, Michael Milior from the Kitware company is actually one of the engineers who has spent most of his time developing and deploying the ray tracing solution in VTK and ParaView. I quote here Michael in one of the articles that he posted on the Kitware blog about screen space ambient occlusion. So our depth perception is highly sensitive to ambient occlusion. What is ambient occlusion? Ambient occlusion is all those regions of space which are somehow hidden from the direct light. So holes, creases, concave surfaces are occluded and they receive less light. The example I have put here on the pictures is a synthetic material, which I have on purpose made very thin with a lot of holes. And it clearly shows the advantage of using SSRO. On the left side of the image, we see the classic OpenGL rendering, where every visible piece of the geometry receives the same quantity of light. But really, in reality, that shouldn't be the case. Let's look now on the right side of the image. If you look deep inside the material, it should be obvious that those visible part of the geometry, even though they are directly visible in front of the camera, they receive less light because they are occluded. Somehow the ambient contribution of light gets diminished for those part of the geometry which are inside the material. So this is really the use of screen space ambient occlusion, and it can be done in ParaView. Actually, it's not the interface is not exposed on the graphical user interface, and that's a little bit of an issue, but it can be done rather simply. So I have the code for that. And by the way, the code I have is inspired from that article on the Kitware blog. So There's nothing I made up by myself. It's all the merit of Michael and his colleagues at Kitware. Basically, in VTK, the rendering can be done with multiple passes. And one of them is called the screen space ambient occlusion pass. So this is the definition we use here. And then that interface, that screen space ambient occlusion pass has a set of parameters. Really, three of them are of importance: the screen, the radius, the bias, and then the kernel size. And then the kernel size is the most important. The kernel size really means how many samples we're going to do. Because what the screen space ambient occlusion does is a set of repetition, multiple renderings, which are then combined together, taking into account slightly different positions of light, if you want. So if we use that following code in our ParaView Python shell, we can activate the screen space ambient occlusion, and the script which I have prepared here on the repository. I will let you do this by yourself. I don't think, unless we have time. Well, yeah, actually, I will do it. I apologize. I'm going to do this demonstration because it's actually pretty fast. So in the ray tracing directory of the repository, you will find that.
Just checking which screen should you be sharing, Jean?
I'm not showing it yet. I'm still on the PowerPoint slide. Yeah.
Sorry.
Thanks, Tim. I was just getting it set up. ParaView minus script equals. Okay. Do you see my ParaView screen here?
No. No, we still see the presentation.
Oh, okay. Yeah. So I have to do this in this particular fashion here. Share this other desktop here. Okay. All right. So now this is what we have.
We don't see the desktop.
Yes, I realize that. Sorry, this is just like yesterday. Okay, I do cancel. That's what I need to do. Share. Okay, there we go. So you should see my ParaView screen now. On the left side, I have, let's concentrate on the left side here. I have my spongy material, okay. This is actually a data set that derives from a project collaboration I had with the ETH Zurich biomechanical department. Professor Arbens and Professor Van Lente were the originators of this collaboration. And as you can see, even though there's a lot of holes in this material, it's really kind of difficult to get a good perception of depth because we are using an ambient lighting which is uniform everywhere. If I switch to the same speed, in fact, I don't see any difference on my computer here, we get a much better perception of depth thanks to the diminished illumination that we perceive inside the material. Now, there's something I have done here for this particular demo. As you see, the two cameras are synchronized. That's a very nice thing to do. I'll show you how to do that, by the way. We have over here. Okay, this would be the standard way of doing things. So, for example, if I start from one rendering view, I get a second view here on the side where I show the same object. The both cameras are independent. If I want to link them together, I do a right button click, I do link camera, and I click with the left button on the second window where I want to synchronize the camera. And now I have my two cameras synchronized. So that's pretty useful to compare models if you want. So this is screen space ambient light occlusion. And it happens, it all happens on the GPU. So it's, if you have, this model is in fact pretty small. We only have a 540,000 triangles. So it's for today's GPUs, it's really a trivial thing to do. By the way, as I rotate the model here interactively, you can see that I'm using a different resolution of geometry. If you want to turn that off, this is an optimization, but if you want to turn that off, you go to your settings over here. Under the render view, there is a parameter called LOD threshold. LOD means levels of details. It sets the data size in megabytes beyond which we use a reduced resolution geometry. So if I want to, as you can see here, my model is 36 megabytes of data, and my threshold is 20, which means that I'm using by default the level of details rendering. If I wanted to avoid that, I could make this a much bigger number. And here now, as you see, I'm using the full resolution model. So that's actually much nicer. There, so that's for the demonstration about screen space ambient occlusion. Now we're going to review really all the steps that are necessary to go from the classic OpenGL rendering to the more advanced ray tracing based rendering. So it's going to be, we're going to go gradually from one to the next. And before I start, this is the page I added this morning. There's a very nice video that you can find here on the Kitware blog, which shows the use of advanced rendering in the mechanical engineering settings. And I'm going to try to show that video. I'll have to share the screen again in a different way. So let's stop sharing over here and share this particular desktop. There we go. And let me play the video for you. So we have an industrial showroom, if you want, with a water turbine, and we can see some pretty nice things here. There is different materials, and there's also the mechanical engineering data. So this shows you that we can really mix and match the two renderings. And I'll finish up with the video. And you can also see the use of shadows, which really help in the perception of the model. We can see, look at different materials. We have some granular material here on the left. We have some glass material on the rooftop, which reflect the light. So all of this is combined in this really pretty amazing video. Here we have a metallic material, okay, as you can see for this this water turbine, and this is what we're going to show this morning. There. Back over here to my presentation. All right, so there's two different methods. You can either use it with ParaView on your own desktop, execute the following script here, pv retracing.py, or on the Jupyter page, you can execute the retracing IPy notebook. Okay, I'll let you decide which method you want to try, which method you prefer. But in any case, I will go step by step here in my presentation. Now, let's look at this, and the two scripts I have given to you here on the previous page, those two scripts are going to generate this particular image here. So let's look, let's analyze what is there in that image. We see reflection here on this prism. We see a fully glass-like reflection of the surrounding context. So the cylinder here and the straw in the cylinder get reflected on the opposite side of the prism. We see shadows here at the base of the cylinder, and those shadows are soft. I'll explain later what soft shadows are. We even see, as you can see here, this very thin cone of shadow, the shadow that is cast by the straw inside the cylinder. We also see here a large shadow area which comes from the prism. So this lets us deduce that the position of light is on the far left of the screen. You'll have to remember that if you want to do realistic shadows, you'll have to place light in particular positions, right? So reflections, we see shadows, we see refractions, and then we see materials which behave differently. For example, the prism behaves indeed as a reflecting surface. However, the ground floor, which is this quadrilateral based floor, does not reflect any light. So it's a glossy it's an opaque material. There. We're going to build up this picture one step at a time. At the very beginning of OpenGL, we implement a technique called Z-buffer. Basically, in Z-buffer, we render all geometries, and for every pixel on the screen, we keep the pixel, we keep the color of the object that is the closest to the camera, to the eye point. So if I look here at the position of my mouse on the prism, of course, that prism does not have anything in front of it. So the color of that pixel is the white color for the prism. If I go on the cylinder hides part of the prism, so the cylinder wins, so to speak. And regardless of the orientation of the surface, we have one given color, and that's what we call ambient lighting. The next step in in enhancing the perception is to add some diffuse lighting. So based on the orientation of the surface, we will get more or less light on the surface. The next step is to switch to ray tracing. So let's review a little bit the terms of OpenGL rendering and ray tracing. In conventional ray tracing, in conventional rendering, what we call the classic OpenGL rendering, we use a process called rasterization. In rasterizations, the triangles of a geometric model get projected onto the screen. Ray tracing, on the other hand, uses something completely different. It calculates the color of pixels by tracing the path that light would take coming from the eye, from the position of the camera through the virtual 3D space. And as it traverses the scene, the light can be blocked by object, can reflect off of another object. It can pass through semi-transparent materials, etc. So this is, I have a little cartoon here showing the process of ray tracing. We really start from, if you want, outside of the screen space. We go through each pixel on the screen. We go into the scene, and then depending on the geometry, depending on the orientation of the geometry, the colors, the materials, we do different calculations for the light intensity. There. So I have now switched from OpenGL to ray tracing. And if I go back a couple of slides, you'll have to look quickly. This is the classic OpenGL, and this is the ray tracing image. So it's a little bit, it's a bit lighter, but otherwise there's no big differences. In ParaView, the syntax to switch to the ray tracer would be pretty simple. There's an enabling flag on the view object, and then there's a switch between for a certain back end. So we have actually 3 back ends available on the ParaView installation on PitchDate. We have the Osprey Raycaster. Osprey is this Intel library which I mentioned already yesterday, which provides the raycasting engine. The second option for the backend is the Osprey Path Tracer, and we will see about this. And then the third option is an option we can use only if we have a GPU allocation on PitchDate. It's based on an optics optics library, which is an NVIDIA provided library. So at this point in time here, my image has no shadows because I have set it explicitly. Views equals no shadow. I'm going to switch to the JupyterLab notebook just for a second to make sure that everybody can also follow if you're doing the JupyterLab presentation. So this will be ray tracing. Let me switch screen. Okay, so on Jupyter at CSCS, we have the ray tracing IPy notebook. Standard stuff like we did yesterday. We import the ParaView module. We get version 5.1. This is very good. We'll set that 1 sample per pixel, and then we create the light. So if you remember, I told you that for that particular scene, the light was far away on the left side of the screen. And indeed, this is light number 1, which I have positioned far away on the left side. This is the Z coordinates minus 150. So this is something you could play with actually. If you change the position of the light, you should see your shadows move around the scene. Anyway, we'll go with the particular light as it is set now. We'll create a render view. And this is important here, something new we haven't seen yesterday. The lights are added in the following way. Render view, additional lights, because by default, there's always one light in ParaView. Otherwise, we wouldn't see anything. So there's a default light. And then if you want to add additional lights, this is the syntax that you should use. here. And then I also add here a material library. We will go through the details of this later on. So let me execute this cell. I've set up a view size of 400 pixels because I don't want to spend too much time rendering. I confirm here that the NVIDIA GPU on pitch date is available. And then there's a number of cells here which I don't want to go through explicitly. They're the cells making up the geometric model. So this is the prism here, which I have called mirrors. It's actually, yeah, one cell of type VTK wedge. And then the rest of it is an implementation detail, really. You could substitute this with any geometry you wish to use. Then I put a couple of cylinders. So the first cylinder is the straw that we see in the image. The second one is the water that we will have. And then, that's it with that. Then we have the plane, which is the reflecting plane on the floor. Then we have a container around the cylinder of water. Then we have, okay, that's the container. And then we're going to show all of those objects in the PV display widget, which we presented yesterday. All right, let me put this on the side. I'm going to create a new view for the output, and I put it here on the side of my window to make it a little bit easier to go through the different steps. Okay. At this point of time, we have no diffuse light, okay, because diffuse was set to 0. Now we switch to adding a diffuse component to the prism. On the next cell, we switch to the Osprey raycaster without shadows, and that's what we get. And you should notice another option, which I haven't mentioned because I turn it on by default. It's the denoising option. Both Osprey, the Intel ray tracing library, and Optics, the NVIDIA ray tracing library, have a denoising, if you want, a post-processor for the ray tracing, because ray tracing by design is a noisy process. So both Intel and NVIDIA have spent a lot of time in creating those denoiser library, and it's actually very, very effective. So I turn it on all the time, and that's my advice to you as well. So we now have a live object. You can move that around, and you see when I was telling you that the ray tracing is a noisy process, we see as we animate the model, we see a very grainy image. That's the noise. And then once we stop animating, the picture becomes really clear. That's the denoising. All right. Oops. Sorry about that. Sometimes my mouse gets a bit crazy here. I need to try to get back to an interesting orientation. That's pretty good. Let me turn on the shadows. So this is cell number 16. There, shadows are on. And in fact, I'm here looking practically in the same direction of the light. So you can imagine that the light is far away at the end of my screen here at 100 at minus 150 in the Z direction. That's my light. Okay, before I go further, I'm going to explain something else. Oh yeah, actually, we can execute the next cell, which is the cell about soft shadows. In the current image here, I have a shadow line which is very abrupt. It's really a binary thing, 0 or 1. We are either here on the left side of the screen completely under the light, or as soon as we cross this border, we are completely in the shadow. But in reality, that's not like this. If you look around in your office, at the objects on your desk, wherever you are following this tutorial, there are no hard shadow lines. Every time there's a shadow, there's a soft boundary, which we call the penumbra, which is a transition from full shadow to full light. And the way we accomplish this with ParaView and Osprey is by setting the radius of the light to a number that is greater than 0. So watch as I execute this next cell, we get now a softer shadow. All right. Let me switch presentation for a moment, and I'm going to go back to this point over here. I am here with no shadows. I switch my shadows and I get hard shadow edges. This is what I explained. In reality, to implement soft shadows, we set the radius of light to be greater than 0. And we go on. So the next step is about doing reflection. And to do reflection, we have to define a material. Using the classic OpenGL rendering in ParaView, there are no materials predefined. So you have to load a material library, and ParaView distributes a material library with some simple materials. That file is called osprey_math.json, and in the Jupyter notebook, which I have created for you, it's actually anchored in one of my personal directory. But I believe actually I've made a copy of this material file on the repository. So you should also have your private copy of the material file. Let's look at the definition of one particular material, which is copper. As you can see on the image here, the prism here is made of a surface that mimics as best as possible the color of copper. So the type of this material is said to be metal. We define a certain roughness, which means in this case that it's a completely reflecting material. Roughness is similar to saying how glossy is the material. So roughness of 0 means fully reflective, and a roughness of 1 means that there's no reflections. Yeah, and then the reflection characteristics of this material is really an RGB, red, green, and blue material, which indicates which color of light the material reflects. So for copper, we did not invent those numbers. Those 3 numbers are given by some official tables of all materials found out there in the real world. So there, setting up the material for the particular object is very simple. We have an Osprey material parameter for each of the representations. Remember, often we use the word rep for the representation of a paraview object. So we can set that to copper. And indeed, if you go to the next step on your Jupyter notebook, you would get a copper material. Next, next demonstration is how to use a material that looks like wood. Now, if we look at the definition of wood, wood is a material that is based on a texture. So what is a texture? I'm going to explain that in a couple of slides. That texture is actually an image, the wood image over here. And I'm going to show you that particular image and then show you the effect of applying the texture on the image. To apply a material with textures, we need the so-called texture coordinates. So what are texture coordinates? If you use your ParaView on your desktop, you can start ParaView, create a plane, just a default plane, a single cell is enough. And by default, a plane has texture coordinates over here. And those texture coordinates is really a tuple of a two-dimensional tuple with a range between 0 and 1. And we're going to see how to apply this. Let's look at the range of those texture coordinates. If we look at the x component of the texture coordinate, we see that the value varies between 0 here on the left side of the screen to red on the right side of the square. If we look at the epsilon component of the texture coordinate, we have something similar. From the bottom to the top, we have a texture coordinate which varies from 0 to 1. And what does that mean? It basically means that we can map as if we are gluing a picture onto this particular square, gluing the two corners of an image onto that particular square to make it look as if we have a real scene, but it's in reality just a single quadrilateral shown with an image on top of it. So here I've selected an image from my laptop. You can put any image, and I'm going to demonstrate that to you in just a second. So let me switch screen for a second. I'll stop this, and I will run ParaView. Over here, I will share my desktop. So there is ParaView, source, alphabetical plane, without changing any default parameters. You apply, and you get a square on the screen. If you look at the information on your plane, you have normals, and you have those texture coordinates over here, so you can color by texture coordinates. Here's the X component, here's the Y component. Now let's go back to solid color. Under the menu texture, we select an image from our directory, and I'm going to select here ETH, there, this image. So I now have a rendering in 3D of this image, which I can move in space completely. Okay, so this is texture mapping there. So please do the exercise on your own time, create a plane and load a texture. You can pick any JPEG, PNG, TIFF, GIF image, and you can move that around. And this is the principle of texture mapping. I'll continue with my presentation. So we've seen texture mapping, and indeed, oh, what I didn't show you, it was the picture of the wood, but you can imagine that to do this material, to make it look like wood, I basically have an image of a piece of wood, and that's how it works. The final step in my rendering is to use refraction. So to use refraction, I did a material definition, and here I have a cylinder that is made of water. So water is a material defined as a type glass with a certain attenuation color, a certain attenuation distance, and an eta, which is the index of refraction. Now, if you remember your physics class, Physics 101, Snell's law, a ray of light gets bent, diffracted, when it traverses a material interface. And the index of refraction is a number that tells you how much is the bending of the light. So for water, that is also an official number from the nomenclature. This number is 1.33. Now, what is important to realize is that as you look at the picture of the cylinder of water, you shouldn't think about this cylinder of water as a volume. I mean, geometrically, it's not a volume. What is important for a paraview is to have the outside surface of the volume of water. Because basically, a ray of light will enter the cylinder, get diffracted, and then when it exits the cylinder, it gets diffracted a second time. But in between, when the light is inside the volume of water, the light goes straight through, just like it does in any other material. So what we see here is really a double refraction, if you want. The light gets bent one time as it enters the volume of water, and then the second time as it goes out. All right. Because ray tracing can be pretty expensive, we have a flag in ParaView, which is called see a double hyphen here, enable tracing, which you should type in on your desktop before running the ray tracing, demo. And for this to be effective, you have to set the number of progressive passes here to a large number. You can set that number to a pretty high value, up to 1,000, up to 10,000, and it will do a recursive rendering, giving you a chance to interrupt the rendering if you want to change the orientation. But if you don't change anything, it will continue to improve the rendering until the picture converges to a full quality image. So we have here on the left side a poorly rendered, a noisy image, and on the right side here, the converged image. Depth of field is the next interesting point. Depth of field is really, if some of you, I suppose most of you have taken photographs with the classic, well, now everybody does it with a telephone, but where there is, of course, with a telephone, a little bit less liberty. But if you do professional photography, the depth of field really is something that helps you bring attention to a particular region of space and then to blur out the rest. So this can be done as well with ray tracing. And what matters is to set the focal distance to a number greater than 0. As soon as you switch that on to a value greater than 0, you'll have depth of field in action. So let's show the demonstration here, which I have prepared for you. This is I've actually prepared a Jupyter notebook for this called the 3T part depth of field notebook. We'll go through it. Basically, on the left side here, I have the depth of field far away, the center of attention far away on the T part. In the middle image, I have the focus on the middle T part. You can see both the far away and the front T part are blurred out. And then on the right side, we have the focus on the front facing T part. So that's for depth of field. And we're going to do this in the demonstration, this particular Jupyter notebook. All right, I'll do this in a second. I'll go back to sharing my...
There's some questions as well in the chat.
Yeah, okay. I will, let me switch the desktop first and then go to the questions, yes. So first question from Louis, how could we modify the properties of these classes? For example, the refraction index of water or the color of a material. Yes, and the question is really about, can we modify the JSON file on the fly on the notebook? And my answer is, I believe not. This is something fixed. You would have to reload, you would have to modify the material file. You would have to modify the material file offline if you want, and then reload the material using, if I look here on the cell number 4, reassign that Osprey material libraries. There's probably a way to do it online, but it would be some pretty detailed stuff. If you think it's actually, I think, yes, it would be a fun thing to do this interactively. I'll have to look if it's not too complicated to do on the fly. But at this point in time, this is not something I have ever tried. Okay, I need to finish up here my rendering. So I was, just before we go to the next demo, so this we had done. Let me switch to, yeah, this we had done. The water, okay, this was the last cell we had to execute, and probably, I don't see any water. I don't know why. No, it's pretty simple. So the answer is there's no water yet. Is because you need to switch to the path tracer to do refractive material. Okay, so there, as soon as I execute that cell, I should have a rendering of water here. It's thinking about it. Okay, there we go. It took a while, but there's some funny things happening to my my rendering here. It's not very clean. This would be probably something that needs to be re-executed. Okay, I don't want to waste too much time on this. Please play with it, and then please report to me if you have problems. So this was the ray tracing demo, and I now want to go to the teapot, the 3 teapot. So I have the same thing here. What I've done basically in this particular cell here is I've loaded the teapot once. So there's the body and the lid, and then I make 2 copies of them. Those are 0. They don't consume memory. This pass array filter is something I used already yesterday. It's something very convenient to make copies of geometries, and then I simply change the position in space of the object. So this enables me to do a rendering. So there is my image here. I'm going to put on the side over here. I'm going to enable raycasting. So there's raycasting with shadows. I switch now to the path tracer to see the glass refraction. At the moment, I have focused everywhere on the image, and then I move the attention, the center of focus, to one teapot and then to the next. There we have a completely blurry image here at the beginning, at the base of my image, and then we have more focus on the far side. If I switch to the center, I have this. And if I switch to the closest teapot, I have this. And I even made an interactive demonstration of this using the NumPy widgets interact. So you can now play with that, change the distance, and change the focus, the focal plane. You see, if you set that to 0, you have a fully converged image everywhere. If you set that to a high value, you have a blurry image. Okay, if there's no question, I'm going to follow up with a couple of concerns which are important for ray tracing. The first one is geometric issues. Ray tracing is really, I would say, at the mercy of the limits of floating point precision implementation. So imagine a liquid, the water in a container. Where exactly is the boundary? I mean, geometrically speaking, is it something like here on the left side where you don't use an explicit boundary between the container and the water itself? Or do you use an epsilon here which separates the two geometric boundaries? Or do you make an overlap as we see here on the right side? Those are very important questions, and you will see that the quality of your rendering will really depend on how precise you are with those geometric issues. So for the cylinder, for example, in my demonstration, instead of using a warped plate, which used to give me an artifact here at the boundary of the cylinder, I use a fully described geometry which does not have internal boundaries. That was the key point, really. The application I showed you yesterday was this particular movie, which I demonstrated yesterday. And then I have one more movie to show, actually. So in practice, on pitch date, if you use ParaView in a client-server fashion, you should use a single node allocation, and then the multi-threaded TBB support on the node will do all the parallelization. So if you use an MC, the data MC partition, you'll have 72 compute threads, and the slurm options to use would be what I have here noted on the slide. And if you use the GPU option, you would have, of course, less threads, but you still have 2 times 24 with hyperthreading. So that's 20. Let me see if I do my math correctly. On the day GPU partition, we have a single core. That's it. We have a single CPU with 12 cores with hyperthreads. That's 24 threads. That's it. And then we applied all of those techniques to a very nice movie last year, which was actually awarded a prize at the American Physics Society Gallery of Free Motion. So I invite you to look at this movie for your entertainment and for your motivation to do the same with your data at CSCS. There, it's 10 o'clock, 10:04. I'm 4 minutes late, but I think still you bear with me. We're going to take a break. I'm going to stay online. And then after the break at 10:30, we're going to talk about PBR, which means physically based rendering. In the meantime, please take a break. I encourage you to ask questions, and then I'll start answering the questions during the break as we all take a few minutes of relax. Thanks. Okay, folks, we're going to start again. I hope you had time to try some of the demos. I had time to do a quick little change to the ray tracing demo, which I'm going to share with you on the Jupyter Lab notebook. So if you are with me, let me share the screen. There we go. Basically, at the very beginning of the presentation, I said that we could change the position of the light to see how the shadows move around. So if you remember, I had set up my my first light position to be at 50, 50, and minus 150. And then I simply just, to have some fun, declared a move light callback here to use with the interact widget of IPy widgets, making that go from minus 150 to 150. And as you can tell now, I can move my light position around, and of course the shadows move around with it. So that's pretty good. That's pretty impressive, actually. And as you can see, as we move the cursor, the picture is very grainy, very noisy. Then as soon as I stop interaction, we get a much clearer image. So that's really good because it can adapt to the hardware that you have available. If you don't have so many computing threads, the computation will take longer, but with the denoiser library, you'll get some pretty good result pretty quickly. Now, a few more tips about rendering, about ray tracing. As you've noticed, certainly, and if you try that on your local desktop, perhaps you've seen that the the performance might really depend on the hardware available, but it also depends on the screen size resolution. So my advice is to start with a small resolution window, okay? Because unlike OpenGL, ray tracing really the performance of ray tracing really depends on the number of pixels, because for every pixel in the image, it will have to do the whole computation. So you can turn off shadows, you can turn off refracting materials. Those are very expensive to compute, and then do a step-by-step setup, just like we did in that Jupyter notebook. First start with the OpenGL classic rendering, then a little bit at a time, add more options, add more materials, add more lights, and then for your final rendering at high resolution, just use the full machine. Okay, I mean the full hardware available and all the ray tracing tricks. But anyway, there is a fun little demo with IPy widgets. Okay. Any final questions concerning ray tracing? Nope. You're all having fun. You all can copy this, can make up your little interactors for that demo. So let's switch now to physically based rendering. Now, introducing physically based rendering with VTK. There's a couple of this first blog article from the Kitware site, very interesting. Really, and I recommend you read that because there are more details given. physically based rendering is really about replacing the classical found reflectance model with something more intuitive, because indeed using an RGB, a red, green, and blue color to specify the ambient color, the diffuse color, and the specular color of a material is just not very, not very intuitive. So using physically based rendering is going to be a lot more closer to our natural understanding of materials and light. And then if you want more details, really this would be for a more advanced audience in computer graphics. There's a nice also PBR theory article that I can refer you to. But on to my next slide. Really, PBR is about specifying a base color of an object. This is also called the albedo of the object, and it's really the perceived color that you see in your object, the so-called diffuse color for non-metallic object, or the specular color for metallic object. And this is being set with a single called set color. And then we have the metallic and the roughness parameters. We've seen that already in a previous demo this morning. I mentioned the roughness parameter of a certain material. So really, in the real world, we make the distinction between metallic or non-metallic object, and then in between, we can play with it in a range between 0 and 1 to make something more or less metallic, reflecting more or less light. So just to make it very concrete, I've made a demonstration Jupyter notebook for that. But before we go into the notebook, I want to add one more thing to this physically based rendering. There's something called image-based lighting. And in image-based lighting, the environment, so the global environment around you, you have to imagine that the geometry, the scene, is in a global environment, just like you are yourself sitting in your office. In front of you, there is a computer. I mean, in my office here, on the left side, I have a window. On the back side, I have a wall. On my right side, I have something else. And then I have something on top of my head and something at the bottom. So there's light coming from everywhere, from all 6 directions. If you imagine that your object is sitting inside a box, a 3D box, which has a left, a right, a top, a bottom, a front, and a behind face. There's light coming from all those 6 faces of the cube. And we can make an image which represents, and this image is called the cube map texture. It represents the view that you would have if you look at each of those individual faces one at a time. You combine all those 6 faces together, and then you get your image-based lighting. So I'm going to switch now to the NumPy notebook, and then we'll play the demo. So just a second. I'll share this again. Sharing. I'll get rid of this, and I'll run my PBR NumPy notebook example. So I'm going to start by defining 3 planes. So I've mentioned 6 of them, but to be able to see my my model, I'm going to define only a left, a front, a right and let's see, 3 faces. Well, that's 3 planes. We'll look at the pictures and it will be simple. And then in the middle, I put a torus. This is a paraview object called a superquadric, and by default, it shows a torus. I'm going to make this in a view and show it inside my standard paraview display. There we go. So there's my classic rendering of a torus, and then three planes. This would allow me, by the way, to do ray tracing as well, and then to show some shadows on the planes. But we're going to keep ray tracing out of the discussion for the moment. If I set interpolation to be flat and zoom a little bit on this torus, as you can see, there's really the same. There's no reflection on this surface, and that's the very basic illumination setup for the rendering. By default, ParaView uses the so-called guru shading, and then with a specular setup, with a specular value of 0.5, as you can see now, as I executed the cell, we have some reflection here on the torus. But you can also, oops, sorry about that, I went off. You can also see that the reflection only happens on the torus. There's no reflection of the 3 planes because those three planes by default have a specular value set to 0. Now, switching to PBR, which would be the third option you have in ParaView, I'm going to define a metallic value of 0.5, which would be halfway between metallic and non-metallic. And then I will define a material with a roughness of 0.9. You'll see that is very, very low to begin with. Then we execute that. Then I'm using my standard interactor for my Pi widget to change interactively the roughness and the metallicity of the object, and you'll see the effect of it. So there is an object now that has taken the color of copper again. If I make it more metallic, it becomes indeed closer to our natural understanding of a metallic surface. If I make it less metallic, it becomes something more like a plastic-looking object. And then if I change the roughness of it, I will make it reflecting more or less light. So this is reflecting, this is not reflecting any light. And as I lower the roughness parameter, I make it reflecting more and more light. Okay, so there's really here a way of adjusting the illumination on materials, which is a bit more closer to reality. Now, to decide on the color of the material, I've used here a color. As you can see, red is 1, green is 0.6, and blue is 0.5. So this is close to the this copper material we had, and you are free to play with different parameters. Now, on the surface of the object here, I am only looking at the contribution that comes from the light sources. But what if this object was embedded into a natural environment like I told you earlier, think about placing this object in its natural environment, and there's light coming from everywhere. And if I fix my viewpoint on the left side or on the right side or at the bottom or on the top, I would see something completely different. So this is what image-based lighting is about. And to demonstrate that further, I'm going to go to the next part of the demonstration. Now, glossy materials. So I'm going to set that to a pretty low value of roughness. Glossy materials are reflecting the environment with something that is supported also by the PBR shading model. And I'm going to load a cube map texture, which I have taken from this HDRI heaven.com website, which has lots of examples which are free to use as far as copyright is concerned. So I've taken here the example, the Palermo sidewalk image, which I'm going to show you with Matplotlib. There, you've probably seen those images around. They look like a picture where it's actually a 360-degree view around your point of view. So imagine taking pictures and then moving, rotating around a vertical axis, rotating your view, taking other pictures and then combining all of them into this 360 view. That image we're going to use as the environment for the rendering in ParaView. So we're going to make the torus completely reflecting all light. So roughness is 0. We're going to hide all the 3 planes. We're going to create a texture with this file name and then use 3 different parameters in ParaView to enable this image-based lighting. The first one is use skybox background, set to 1, use environment lighting, and then set the background texture to cube. So there it is. So we now have the impression of navigating through this external scene. And it's really just looking at this texture. There's the red car. Excuse me for a second. Let me stop the camera. There's the red car, which is at the center of our image here. If you look at the image plot from the center image here. And as I move my viewpoint, I'm just going around the scene. And if I zoom now on the torus, you can see that the torus, the material, reflects the surrounding light, the surrounding scene. Yeah. There we go. So this is image-based lighting. And if you refer to the video that was made, wait a second. I'm not sure if the video the video example I gave you from this water turbine was also using image-based lighting. But you can imagine now that how you can make something really a lot more appealing in terms of presentation if you embed your sim, your simulation with a picture of an outside environment that would be close to reality. So this is image-based lighting, and it's available in ParaView as of version 5.8. Now, the you're welcome to try any cube map textures from that particular website. Now those pictures are stored in HDR format, and for version 5.8 of ParaView, you'll have to convert those images to make textures. You'll have to convert them to JPEG. But when ParaView version 5.9 will come out, and this will be next, at the end of this month, I expect to have the first release candidates available on PageStained. We will be able to load directly the HDR images, cube map textures into the scene. So I let you play with this. Something you could try is make the planes visible again, okay, and then change the viewing parameters for the planes to make them also reflect the outside environment. So if you recall here, I have changed the interpolation method for the torus. What you would have to do is do the same for the planes and then change their metallic and roughness components. And then you would have in your scene a rendering of the outside environment also reflected on your on the three planes surrounding the torus. So I leave you with this as an exercise, and I want to take the last 10 minutes we have in our scheduled time to go back to a question we had yesterday, and I glossed over it pretty quickly. This was the import of NumPy arrays into ParaView. Before I do that, I'll check that there's no questions concerning this image-based lighting and the PBR, physically based rendering. So I have two questions, in fact. Okay, Louis was asking something about zooming, but I guess he resolved the question by himself. Yeah. So zooming in, which I'm doing here with my middle mouse button, indeed only changes the position of the camera with respect to the object, but the global environment, which is based on this cube map texture, doesn't change. You would have to move around in this particular way to navigate through different viewpoints and see your background image from different viewpoints, okay? Very good. All right, let's quit this. And let me go back to ParaView, the ParaView folder. I have here a NumPy array ParaView import notebook. And this is basically an example on how to import NumPy arrays. NumPy arrays, Dask arrays, you can, I mean, anything that has the shape of a NumPy array, you can import directly into VTK object. And what matters is that this does not make a physical copy of your arrays, but it makes a smart copy, i.e. you are reusing the same memory location as the NumPy array. And trust me, I've done the experiment on my laptop using a 16 gigabyte NumPy array, and nothing happened. ParaView didn't crash. I was able to reuse that 16 gigabyte NumPy array directly into a VTK object. Now, when we talk about importing a NumPy array into ParaView, what is important? Certainly, the shape of the array is important and the size of the array. So suppose I have a 40 by 40 by 40 NumPy array. That array could actually fit into different VTK object. It could be a regular grid, it could be a rectilinear grid, or it could be a structured grid. So the decision about how to map an NumPy array to a VTK object is really your responsibility. You'll have to understand closely the difference between a regular grid, a rectilinear grid, and a structured grid. In fact, yeah, so that's the first thing. Now, a VTK image data, as we showed yesterday, is defined entirely from an origin and a spacing. The spacing is given as three numbers, one in the X, one in the Y, and one in the Z direction. And that's all we need to define a regular Cartesian grid. As far as rectilinear grids, we have to give as input three one-dimensional arrays, each for the X, Y, and Z coordinates. And that's how we defined a rectilinear array. And then as far as structured grid, we have to give explicit X, Y, Z coordinates for each point in our geometry. So the interface I have created here reflects exactly those differences. If I look here at this first class definition, which I have defined for structured grids, we can here define the coordinates of the structured grid given three independent 3D shaped arrays for X, Y, and Z. And then we set the dimensions over here. Let's see here. We set the dimension of that mesh to the size or the shape of the coordinates array, if you want. There we go. That's the first definition. For rectilinear grid, we give arrays which have a shape of 1. So they're 1D shaped array for each of the axes. And then the last example is the point set from arrays. This is really a point cloud, which does not have connectivity, but it still has coordinates in 3D. So for those coordinates, you can give either a three-dimensional NumPy array of coordinates. This is what I give here to the set v coordinates function call, or else I can give three independent arrays for X, Y, and Z. Now this interface I have made here, those class definitions are really just a first draft of what a more advanced NumPy importer would be. There is in fact an example of a very advanced importer, which is given by Paraview itself in VTK. In the utility module library, there is a VTK image import from array class, and I encourage you to look at the source code of this class to see how it's implemented, because it really takes care of all possible dimensions and types of NumPy arrays which can be imported. Now, to demonstrate this, I have the following notebook, which I'm going to execute pretty quickly. So the first demonstration is using a regular grid, and that's the grid we are very familiar with from yesterday's experiment. That's a fully regular uniform grid, which I'm coloring by the variable called scalars. I'm going now to hide this object and build a rectilinear grid. So to build a rectilinear grid, as you can see, I have x-axis, y-axis, z-axis defined as a 1D shaped NumPy arrays. Here I have 3 different definitions, and I give those as dimensions. This would be my rectilinear grid. Let me put this on the side here so that we can browse further down our notebook. I'm going to hide this. Do now a cylindrical grid, which I need to reset. There we go. This is the typical curvilinear grid, which we are familiar with. And then the final example is the point cloud. I'm using NumPy to create a set of random coordinates of shape, number of points by 3. And that data is rendered over here. Here I forgot to hide my previous producer, and I'm going to reset my camera, and I still have another grid in the way, which I'm going to hide. Let's see, I got a bit confused. I still have my my regular grid here in the middle. But anyway, now the question came up yesterday evening: how do you save that data? And I was confused. I was using the wrong object proxy. In ParaView, you have a function predefined to save the data, and if you are in the ParaView GUI, usually you have one object that is selected in your pipeline, and that object is the active source. So by default, the Save Data menu saves the active object. In our particular case here, in this particular pipeline, we have multiple objects that have been created, and those objects are the trivial producer objects, which are ParaView objects, and I can pass those directly as proxy to my save data function. So I've created one uniform grid, one rectilinear grid, one structured grid, and one point cloud. I can save them to disk in this particular fashion. Now notice that for each different grid type, I actually use a different suffix here. VTI stands for the XML-based VTK format for VTK image data. VTR is what we use for rectilinear grid, VTS for structured grid, VTP for polydata. And if I were to, for example, use a VTK option like this, this would use the legacy file format of VTK to save your data. So depending really on the file name that you give, ParaView will be able to dispatch the saved data to the appropriate file format for the data that you have on hand. There. So just to finish up, I have not packaged this particular class definition for the importers for structured grid, rectilinear grids, and point clouds because it's not a mature interface yet. I want to give people an exposure to it. You are free to contribute to it. We could work together, for example, on making sure this works for not only 3D, but also 2D and 1D grid structures. I think it works pretty well for 2D. I have done some brief testing of it. What is missing is currently is that it assumes that the NumPy arrays are arrays related to the node of a grid. But as you know, in ParaView, we can also have data based on the cell centers. So it would be very trivial to add that functionality to be able to import NumPy arrays related to the cell data of the different grid type. And then there are certainly some issues about data conversion because not all NumPy D-type arrays can be imported directly into the VTK object. So there is some fine tuning to do. So if any one of you is interested to work with me, we could certainly make this a more mature interface and then make it available for the community to use. There, this is what I have to say for now. I have one question concerning the color of the background in ParaView. So I'm going to answer that question right there on the notebook. The view, I forgot its name, so I'm going to say get render view, which is my active view, and then that view object should have a color called background color. Let's see if I remember. No, it does not. Let me think about it because I should be able to use the, there we go, background like this. Okay, that's the default background. And to set it differently, if I wanted to say something red, I would use one like that. Okay, so this is changing the color of the background. Now, red is not a good background, by the way. Don't use it if you can. use something different. All right. There are different ways to do backgrounds. As you noticed, I have two different colors. One of them is background, one of them is background 2. Let's look at its set up to 0, 0, and 0.1. And if I set view.use gradient background, which is by default 0, if I set that to 1, it does a gradual interpolation, a linear interpolation from the first color to the second color. So this is another way to do backgrounds here. As you can tell, I have now graded shades from red to this second color. There. I'm going to stop my presentation here in an official manner, and then I will stay open. I will stay connected for further questions if you have them. Okay, good. So this is the end of our presentations for yesterday and today. please do send me personal emails, or if you have, if you prefer, send your questions to the help desk at CSCS. If you have something, if you have questions related to the installations of ParaView at CSCS, how to run Jupyter notebooks. I mean, all those things we can try to resolve. We can resolve with you in the next days as you try more of those exercises, as you try the notebooks I have provided as demonstrations, and as you try to apply those to your own simulation outputs. So my wish is that this has been useful, and that you will be able to use ParaView or VTK Python programming to do this mix of deployment between Jupyter notebooks and straight ParaView scripts. As you recall, yesterday morning I presented very briefly, I presented other 3D applications such as Visit, and I presented also the use of VNC remote desktop to do OpenGL rendering. So if some of you are interested in using different OpenGL based applications, for example, I know some people are using Blender here on the CSCS machines. So it certainly can be done. Using Blender, you would have to use an X server. So this would be done similarly to allocating a VNC remote desktop. Otherwise, I recall a question from yesterday about doing SSH forwarding with a -X flag. This is not recommended to do rendering on the CSCS architecture. In general, with ParaView, because ParaView has an optimized method to transfer images between the client and the server. So using SSH forwarding would by far not provide the same performance as the optimized image transfer layer that ParaView has. So I absolutely recommend that you get the client server connection set up running smoothly. I have one more question here to ask. Julia is asking, is it possible to see the Q&A after the tutorial? Some questions could be relevant to colleagues watching the videos later. Indeed, this is a good request, and we had that issue already in the previous webinar, and the answer is no. I mean, what I can do is I can try to recall some of the questions that were made and then write them up, but we don't have, and technically speaking, we don't have a recording of those Q&A sessions after the session is closed, unfortunately. So again, I encourage you to send me an email with a question that you asked, for example, and then I would rewrite my answers for the benefit of your colleagues. So I have a question from Luis. Yesterday we went through a lot of material. In order to consolidate all the knowledge as better as possible, how would you recommend us to proceed? I think we should. I think you should really look at applying this directly to your simulation project at CSCS. I mean, I assume most of you have an allocation project at CSCS, and in that case, I would be really happy to follow up with you. Start with the first output of a simulation. Discuss the data format, test and evaluate if parallel visualization is really necessary, because there's actually quite a few cases where we can do visualization very well on a single node, and then evaluate what are your needs in terms of animation and in terms of replicating a visualization scenario. What I do recommend, however, for all of you is that you use the Python interface to ParaView. Let me give you an example here. I'm going to switch screen, and I'll give you an example, because the thing about the Python interface is that you can easily share your interface, share your script, reuse bits and pieces from previous scripts, etc. So I've loaded. Let me switch screen. There we go. This is the demo we've done earlier with 3 planes and the superquadratic. If I save the state, the ParaView state, with the default option, which is this PVSM option, I'll call it state.pvsm. I'll show you what the script is, what the output is. There's the state. It's nearly impossible to find the torus, to find the planes, and to find anything you want about reusing bits and pieces of that particular state. Okay. Now, of course, it works. We can reload that script. You will see how I can run ParaView and use the load state like this. But actually, there's my layout. It works fine, but it's impossible. I never use the state files when I work with users, because I cannot share the output of the visualization scenario. On the other hand, if we look at the Python code for the same, I have something a lot easier to read. Okay, there's one plane with an origin and a resolution. Here's a second plane. Here's a third plane. Here's a superquadratic with resolution defined, and then the show command we've seen previously. Here's the show plane, etc. So this is very, very much more useful in terms of sharing work with different colleagues. When I reload that particular script like this, I get exactly my superquadratic object with the resolution, just like I have said it in the Python script. And I have my planes with the origin, the point, etc. So in other words, the Python API reflects exactly what you see on the GUI. So a lot easier to reuse. That's my bit of advice. Let me finish up here, since we have the live demonstration of the torus here. Using the graphical user interface, I would go to the skybox background option. I would load my texture. Here I'm going to use a cloud texture. And there I am again in an environment where it looks, I mean, this is a pretty, this is a low resolution image, but it looks like we are outside in an environment which is given by a cube map texture. Now, if I zoom over here, I make those surfaces invisible. I can now edit the metallicity and the roughness of the object. And I need to use that as environment lighting. And now I have a reflection of my environment onto the surface of the torus. And if I change the color of the object over here, I can make this any color I wish. There it is. There's a blue torus reflecting my environment. I look at the questions. Let's see. A couple of questions. No, that has been answered. So, okay. Folks, don't be shy. If you have questions, we'll be here 10 more minutes and we can try to answer your questions. Otherwise, I will be checking my email if you have more personal, more personal questions. Okay, so folks, I have, let me see, a couple more questions. People are asking me about more tutorials. So I know that the IEEE Visualization Conference will have a tutorial, I think in the coming weeks, and those tutorials this year, exceptionally, because of the pandemic, they are free for all people. So I think you should look for IEEE visualization tutorials, and there is a ParaView tutorial that will take place. Otherwise, there is an online tutorial actually, which is also of great interest. So you should Google for ParaView tutorial and you'll find it for sure. There's Alex asking me about SSRO, screen space ambient occlusion, and asking about is there another types of ambient occlusion? And here I'm a little bit hesitant to answer. I believe yes, there are other types of ambient occlusion. I believe that the screen space refers here to a technique that is indeed that comes from the screen. So it's more of an image processing based technique, whereas I believe uh, there are techniques based on a different type of iteration through the ambient occlusion equation. So I'm not quite sure about this. In VTK, what we have is screen space ambient occlusion. It's not directly exposed in the ParaView interface, as I have told you, but can be turned on and off in ParaView using the Python code I have provided. What I'm not sure is about how to use this in a parallel rendering manner, because in parallel rendering, ParaView does a compositing of images where each ParaView server does its own rendering of a subset of the data. And because each ParaView server has only a subset of the data, you would imagine, it's easy to imagine that you cannot have the complete occlusion seen by each object in a scene if you have partial data sets. So this, I imagine, would not work in a parallel setting. Okay, very good. So I will close this session. I thank you, all of you, for participating. I thank my colleagues at CSCS, in particular Rafael and Tim, who have deployed the Jupyter Lab stuff on pitch date. And I give you appointment for all of those interested with Samuel and myself next week for a webinar on I/O, dedicated to I/O. Okay, so good afternoon now to all of you, and again, don't hesitate to send your questions for collaboration with me